protoplanetary disk. And then in the protoplanetary disk, these dust are accreted to make planetesimals, which is actually nowadays asteroid is the remains of planetesimals. And most of the meteorites came from asteroids. So that's why the meteorites containing much information about the early solar system evolution. So some meteorites containing organic matter, and these organic matter are also important to understand the chemistry in the early solar system, and also important in the aspect of origin of life, because this organic matter can be brought to the early Earth in meteorites, and also interplanetary dust particles. They are kind of small meteorites. So this slide is actually kind of similar to the first one, but more focusing on the chemistry. So this icy dust evaporated and recondensation in the inner side of the protoplanetary disk, and some ice are survived or to form icy planetesimals beyond the snow line, and some contains the interstellar chemistry, and some are also mixed and recondensate ice. And the planetesimals containing ice, then they are heated mostly by the decay of aluminum-26, and then the liquid water circulated in the inner part of the asteroids. So the liquid water reacts with anhydrous minerals to form secondary minerals, such as hydrated silicate, like phyllosilicate or carbonate, and so on. And further heating causes thermal metamorphism as well. All these processes cause diverse in the meteorite. So actually there is a large diversity in meteorites. The most primitive class of meteorites are so-called carbonaceous chondrites, which is known to contain organic matter. So carbonaceous chondrite actually has several groups, like Ci, Cm, something like that. So most primitive kind of carbonaceous chondrites are Ci, Cm, and Cr chondrites. And so I put some numbers in here. These are so-called Petrologic type. It's this is a degree of aqueous alteration and degree of thermal metamorphism. So talking a little bit more about, So for example, the Murchison meteorite called CM2 carbonaceous chondrite, a group CM group with Petrologic type 2 chondrites. So I talk about a little bit more about Petrologic type. So if you have experienced aqueous alteration, the Petrologic type will be 1 or 2. So 1 is much altered compared to number 2, type 2. So type 3 considered as a primitive one, but actually most of the type 3 chondrites experienced thermal metamorphism. And type 4 or more are heavily thermally metamorphosed chondrites. So basically, organic matter only exists in type 1 to 3 type chondrites. So most primitive type of carbonaceous chondrites contain up to a few weight % of organic matter. Some part are so-called soluble organic matter, which is extractable with solvent, methanol or water or something like that, including carboxylic acids and amino acids and so on. The majority is actually exists as insoluble organic matter, so-called IOM, which is collected after acid demineralization. So these are very complex in molecular structure. This is a model structure of IOM from Murchison meteorite. Containing aromatic cores with bunch of functional groups, like aliphatic or carboxyl, something like that. So looking at morphology, this is TEM image of IOM. It's containing a fluffy kind of IOM. This is actually, most of the IOM consists with fluffy type, and some globule shaped one observed. But globule only about 10% of the volume of the IOM. But fluffy one only detectable after acid demineralization. You cannot observe even in TEM because they are very fine and spread into the mineral matrix, mostly ferrosilicate. So the molecular structure of this IOM is very sensitive to the parent body process, like thermal process or alteration. So the structure changes as heating, by heating. For example, the aliphatic part decreases with heating, and also carbonyl part decreases with heating. So this is basically reflects the aromatization or loss of branching, aliphatic branching, or this kind of carboxyl structure by heating. So looking at the soluble organic matter, they are very diverse in structure, and recent results show that tens of thousands of different molecular compositions exist in a single meteorite, Murchison meteorite. So this is only molecular composition. So if you consider the molecular structure, it will be millions of diverse molecular structure exist in single meteorite. So now we more focusing on the amino acids. This is a comparison of amino acids abundance and relative abundance of amino acid species in various meteorites. So the moderately aqueous altered type of meteorites, like CM2, CR2, CR3 chondrites, they have most amino acid abundance, and mostly in the form of alpha type amino acid. But if you experience more aqueous alteration, the amino acid abundance decreases, and also the portion of alpha amino acid decreases and relative abundance of gamma and delta amino acid increase. So this is basically same thing if you experience thermal metamorphism. So in the case of thermal metamorphism, the amino acid abundance also decrease, and alpha amino acid portion is decreased as well. So that's the basic idea of what caused parent body process to organic matter in meteorites. So next, what's the origin of the organic matter? There are several hypotheses to make various organic matter. So first, in the molecular clouds, there are UV and cosmic ray irradiation on interstellar ice can be produce various organic species. And also in the protostellar nebula, so-called Fischer-Tropsch type reaction in gas and dust, solid dust like silicates or metal dust can also produce complex macromolecular kind of organic matter. And finally, in the planetesimal phase, especially during aqueous alteration, also various organic matter or complex organic matter can be produced from simple molecules. So I think each process contributes to make very diverse suite of organic matter in meteorites. But now we are focusing on the process in planetesimals. So, especially in the aqueous alteration process, it's good to make chemical reactions because the exist of the liquid water is very good to organic chemical reactions. And also there are various small molecules from molecular cloud or planetary nebula origin. And minerals, surrounding minerals also act as a catalyst to form various organic matter. So the co-creator proposed to form macromolecular organic solid similar to chondritic IOM from Holmos reaction using formaldehyde. And also we further studied this reaction adding nitrogen, adding ammonium, and actually ammonium enhances organic solid production, and also there are significant incorporation of nitrogen in the products observed. So formaldehyde and ammonia is very common molecules in interstellar medium and comets as well. So we can expect they are abundant in the early stage of planetesimal formation. We did simple heating experiments using formaldehyde and glycolaldehyde, which is actually a dimer of formaldehyde, and ammonium with calcium hydroxide, which is a catalyst. So after heating at this temperature, 19 to 50 degrees C, solutions colors are changed into dark brown, and there we can make solids. We did several different analyses for solid and liquid parts as well. So I introduced some part of the result. So first, looking at the yield of the organic solid. They increase as temperature and time. So actually, it acts like Arrhenius type behavior. So we did kinetic analysis of the yield of the organic solid. So this is a time temperature diagram for organic solid formation. So assuming that the reaction mechanism doesn't change in these temperatures, so even at 0 degrees Celsius, the organic solid can be formed in the 100 years or so. So considering the aqueous alteration period is about 10 to 7 years, 10 million years at 0 to 80 degrees Celsius, it is fair enough. It's enough time and temperature for make enough organic solid. And even at the comets, some comets could have liquid water at 10 to 5 years or so. So in that case, even in comet, maybe you can produce this kind of organic solid. Then looking at the molecular structure of the organic solids, they are carbon-13 NMR and FTIR. Black spectrum shows IOM, and the red one and the blue one are experimental products, organic solid with and without ammonium. So generally, they are very similar spectra to the IOM. And then looking at the morphology of the organic solid. So some show spherical shape, like few micrometer in diameter. So comparing this kind of spherical shape is indicate hydrophobic formation of this organic solid. And also compared to the IOM in meteorites, they also contain globule kind of organic matter, but much smaller than the experimental products, actually. So also we can make fluffy organic solid as well. But so far we don't know how we can control the morphology, fluffy or spherical form. Okay, so next we are looking for the liquid phase. First we did amino acid analysis in the liquid phase. So this is HPLC result of liquid fraction made by 150 degrees C experiments. So they have some glycine, alanine, and beta-alanine, and some other amino isobutyric acid and aminobutyric acid are also produced. So they are the results from various temperature experiments. So basically, the products of the products are about the same in 90 and 150 and 20 degrees Celsius, but much less in 250 degrees Celsius. And alanine are larger than glycine, but other one is less than glycine. And they are mostly after acid hydrolysis, but we did we did analysis without acid hydrolysis for 150 sample, and we get some amino acid, alanine, and a little bit glycine, and beta-alanine, but less than the product after acid hydrolysis. We did also DL analysis for some amino acids, and they mostly D and L ratio are same. So this is not contamination from terrestrial amino acid. Looking at the effect of minerals, this is a very preliminary result from one of my students. This is a little bit different starting material from previous one. But generally, if you add minerals like momonite or olivine, enhance the yield of beta-alanine, but not significant for glycine. So going back to the amino acid abundance, this is amino acid abundance relative to glycine without mineral. So generally, as carbon number increases, the abundance is decreased. But alanine are larger than glycine. And look at the gamma aminobutyric acid. So they increase as temperature increases. And compared to the chondritic amino acid, so compared to the CR chondrites, they show generally similar trend. And also compared to the CM chondrite, which is more aqueously altered than CRs. And this is also kind of similar trend, except this one. And compared to Orgeo meteorite, which is more aqueously altered meteorite, so they show a little bit increase of beta-alanine and decrease of alpha aminobutyric acid. So in general, roughly similar trend with aqueous altered chondrites. And now compared to the thermally metamorphosed chondrites, like CO or CV carbonaceous chondrites, they show some variation, difference between experimental product and thermally metamorphosed chondrites. So the beta-alanine are larger, much larger, and alpha aminobutyric acid are smaller. And also gamma aminobutyric acid are larger than lower temperature products. So this is consistent with the increase of gamma aminobutyric acid with temperature increase. So this is probably due to the thermodynamic stability of each amino acid. So thermodynamical stability is gamma aminobutyric acid thermodynamical stability is larger than beta-alanine, and beta-alanine is more stable than alpha aminobutyric acid. So amino acid could have been produced in aqueous environment in planetesimals, and then extend aqueous alteration and or thermal metamorphism may destroy labile amino acids, and then the relative abundance of strong amino acids are increased. Okay, so in summary, there are a very wide variety of organic matter exists in meteorites, mostly in primitive carbonaceous chondrites, mainly in the form of insoluble organic matter, and some also contains amino acids as well. So origin of these chondrites could be, these organic matter can be various. And we are focusing on the process in the planetesimals, and we did experiments simulating aqueous alteration using formaldehyde and ammonium and water. So they can, we can form IOM-like organic solid, as well as various amino acid species, including alpha, beta, gamma amino acid. And the trend is similar to the one found in aqueous altered chondrites. Thank you for your attention.
Okay, we are up for questions now.
Thank you. Hey, Yoko. This is a very nice talk. Thank you, and good to see you again. The D to L ratios you measured are actually pretty high. Is
Yes.
that reproducible, and do you have any explanation?
Actually, we could only do once this DL analysis, so it's not that so precise. So I cannot say this is this high value is real or not. So we need more experiments to do that, to show that.
Yeah, there's some theoretical work that tries to predict what the original amino acids were in life, not the 20 we have now, but maybe some smaller set, 16 or 8 or 10. And I'm wondering to what extent your analyses of amino acids can talk about, is there any, I don't know, way in which there's a connection between the relative abundances of amino acids in us here today or more earlier life and these meteorites?
You mean?
Well, for example, glycine it's made very easily. The abundance of glycine is very high.
Mm-hmm.
Is abundance of glycine in life very high, or the relative abundances? Is there anything that can be correlated between these two examples of amino acids?
Actually, in meteorites, there are not large part of the meteoritic amino acid is non-protein amino acids. So not actually directly related.
I heard in Murchison, for example, I thought that there were 8 of all the many, like 80 amino acids. There were 8 of them were protein amino acids. Now, are those 8 that were in Murchison, are they some of the more abundant ones in life on Earth?
I'm sorry?
Are those 8 that was in Murchison, for example, are they some of the ones that are most abundant in life on Earth?
I think glycine is most abundant in Murchison, but
how about what's the most abundant amino acid in you?
My experiments, alanine
No,
is
your
most
body,
abundant.
my body, life.
Sorry.
I know.
Actually, I don't know much about this thing. I want to ask.
Okay, thank you. Thank you.
Yeah.
Loud enough, it doesn't matter. But all right, the synthesis you do are in water, obviously, and there are materials that are certainly made outside the snow line, so that you get plenty of water in the asteroidal material, and there are materials that are made inside the snow line where you would expect very little water in that case. Would you expect a fundamental difference in the amino acids that you produced outside by the aqueous processes versus inside where they might be remnants of things or whatever? I'm not sure that there is something like that detected, but I'd like to know.
The stone, so most of the organic matter only found in aqueously altered meteorites. So, like ordinary chondrite doesn't contain much of organic matter.
No, but it does have some.
Yeah, that does have some. And this kind of primitive ordinary chondrite actually experienced aqueous alteration. And also, there is another possibility to produce this organic matter in ordinary chondrite. It could be totally different process. It can be totally different process, I think.
No, I agree, but in that case, you would expect a different distribution, for instance, of the amino acids. And I was just curious whether or not that comparison had been made. I don't know.
Actually, ordinary chondrite have kind of different distribution of amino acids, like gamma or delta amino acids are higher compared to the other one. It can be, like I said, it could be because of the thermodynamical stability, but also it could be the formation process can be totally different. So there are many possibilities to produce this kind of difference. So I cannot say this is the single answer. It could be the other answer as well.
Okay, I have one. You showed groups of meteorites, right? How accurate are these groups actually nowadays? Because you have some meteorites which are unclassified. So how can you, do experiments, or you have any suggestions?
Yeah, actually, I think it's a good point, because most of the grouping is based on mineralogy or like isotope, or not based on organic matter. So this is not always consistent with observation with organic matter. So I think like Cornell Alexander tried to classify it using organic matter or so. So it should be more work to be done using organic matter, I think.
Okay, do you have, Victor?
Sorry, correct me if I'm wrong, but it seems like you're using a system that could work on Earth. So why do we need to link it to meteorites? So in terms of the origin of life, I mean, in terms of chemistry, it's brilliant. But in terms of the origin of life, is it possible that we just are doing everything on Earth and don't need to worry with meteorites at all? Or do you think meteorites were crucial for the origin of life in terms of delivery of substance?
This kind of reaction can be occur in like ocean, but most of in ocean, the precursor species were diluted. So in the case of asteroids, you can have condensed formaldehyde or ammonium. So that's why I think it's better than early oceans for this reaction.
Do you have any last questions? All right, let's thank the speaker.